So today we will cover the topic of mass transfer, basic aspects of the mass transfer. Okay, so mass transfer deals with transport of individual species in a multi-component mixture. So if you have a mixture with several species constituting that, mass transfer deals with the individual transport of all the species as well as the transport of the entire mixture itself. Okay, so we need to, unlike a single component, say for example, a flow of oxygen or nitrogen individually, as a mixture how it flows, that needs some additional aspects to be covered. So that is what we are going to see in this. Okay, so let us take a simple case of binary mixture. So binary mixture, two species contribute to that, species A and species B here. So species A and species B. In this you can see that let us also simplify the problem further by taking the transport in only one direction, so x direction only, so one dimensional. Later we can expand it to several other things. So if you take the transport of species, a mixture where the species A and B are present and in one dimension, so x direction, the mass flux of a species, that is the mass flow rate of a species per unit area. So that is mass flux of a species A. So let us take species A for example, and the unit of the mass flux is kilogram per meter square second. So mass flow rate kg per second per unit area, so per meter square. So this is written as the mass flux of species A is written as the sum of mass flux of species A, which is due to the mixture, flow of the mixture, so bulk flow what we say. So the mass flux of species A associated with the flow of the bulk fluid or the mixture. Okay, so A and B constitute the mixture itself is flowing at the velocity v, and the A is transported, species A is transported along with the mixture, so it has a contribution due to the bulk velocity of the mixture. So that is the bulk fluid motion, that is one component. Second component is the mass flow rate associated with the diffusion. Okay, so what is diffusion? So that is what we are going to see now. So diffusion, let us take what is called ordinary diffusion for example. So for example, consider a bottle of scent, okay, perfume, which is open in a corner of a room. Okay, so slowly you will feel that there is no like airflow or fans or anything on. So in a very quiet atmosphere of air, stagnant air, the perfume bottle is opened in one of the corner of the room. So what happens is slowly you will see that the perfume is propagated to the other end of the room, that is the entire room will now feel room refresher for example. So this is because of what is called diffusion. There is no bulk motion at all of anything. So air is still, the perfume, you are just opening the bottle so that the perfume has a higher concentration near its source, at the top of the bottle, near its source it has higher concentration. Elsewhere the concentration is very low or zero initially. So due to the concentration gradient, the perfume is transported equally in all directions basically. So if you keep it in center of the room, you will see that it will equally propagate to the entire room. Okay, so this transport of this particular species due to the gradient in the concentration. So it has higher concentration at the source where the perfume bottle is kept, and elsewhere surrounding it the concentrations are initially zero and slowly the perfume travels equally in all directions, and you know that it is a very slow process. It takes some time before which you will not be able to sense the perfume. Similarly, a leak of say LPG gas in a kitchen, slowly you will see that it's actually odorless gas, but for commercial purposes some odors are added. So that particular LPG basically you can see that smell coming out slowly, it diffuses slowly. Okay, on the other hand, if you keep the scent in particular corner and also have a fan just besides that, then you can see that the perfume will be transported at a faster rate in the direction of the flow which is imparted by the fan. Okay. So, the fan actually causes airflow to go through a particular direction. Okay. The concentration gradient makes the species diffuse slowly in all directions, but if you have a velocity in a particular direction, for example, then the bulk flow, which is the convective velocity, that will transport the perfume towards that direction at a faster rate. So, convection of the, if there is any convection present, that will transport mass. If there is no convection present, only by diffusion the mass is transported, the perfume is transported towards this. After a particular thing, after a particular time period, you will see that the concentration gradient ceases, or the concentration gradient becomes constant. So, there is no more transport possible for the in the diffusional way, like the concentration gradient will be constant, then there will be no transport possible, or it becomes 0 or reduces. So, if you take the convection additional to the diffusion, you can see that the transport is faster. So, in general what we consider is a species, the species A in this case is transported due to the convection. If you assume that the mixture which is constituted by species A and B move at the velocity v in the x direction here. So, v is the velocity of the mixture in the x direction, then the species is transported due to the bulk velocity. So, that the first term here is the representation for the species which is transported due to convection in the direction of the mixture flow. Okay, then I told about the concentration gradient. Concentration can be the concentration or the mass fraction or mole fraction, anything. So, here we have written the concentration in terms of mass fraction. So, everything is connected basically. So, the mass fraction gradient in the x direction, dya by dx, that is the concentration gradient in the x direction, that actually that represents the concentration gradient, and you can see the negative sign here. Negative sign here represents that in the direction of the diffusion gradient, the concentration decreases. So, the gradient is negative, the concentration decreases. It is same as the heat conduction. Okay. Heat is conducted from a high temperature point to the low temperature point. Okay. So, the gradient in this particular direction is actually negative, dt by dx is negative if the heat is conducted in the positive x direction. So, similar to this, you can see that the concentration gradient represented by the mass fraction gradient dya by dx is negative. Okay. So, the diffusion of the species A into species B, here we are only considering binary, though the mixture has only two species A and B, like air, oxygen and nitrogen, similar to that. So, the gradient, concentration gradient drives the species A into species B from the point where its concentration is higher to a point where it is lower. So, the diffusion is proportional to the concentration gradient, like the heat conduction is proportional to the temperature gradient. The constant of proportionality is nothing but rho into dAB. Rho is the density of the mixture, and the dAB is the binary diffusivity. I have given here binary diffusivity of the mixture. It is very important property. If you take any pair of species, say AB, okay, then the binary diffusivity of the mixture, the binary pair DAB is a fundamental property which is which represents the rate at which the species A diffuses into species B. This is like the thermal conductivity. If higher the thermal conductivity, the heat conduction will be higher. Similar to that, if higher the value of rho into dAB, higher will be the diffusion transport of the species A into B. Okay. So, now the left hand side represents the mass flux of the species A. Okay. That is density of the species A, rho suffix A, multiplied by the velocity of species A, VA. Now we have to understand that I am introducing one more velocity called species velocity. So the VA is called the species velocity. Rho A is density of the species. So rho A plus rho B will be the total density. So that is what is given. The mixture density rho in the binary mixture, binary constituents will be the constituent of A plus the density of the constituent of B will be the mixture density rho. Okay. But VA, small v suffix A is the velocity of the species A. So let us take a duct for example, and let us say the circles are species A. Circles represent species A, and say square represents species B. So this is a binary mixture. So there are several molecules of A and B which is there, and there is a flow. This is the x direction. So this is x direction, and you can see that the velocity of the mixture in this direction, let it be v, like what I have written here. So this is the velocity of the mixture, capital V is the velocity of the mixture in the positive x direction. So it's one dimensional. Now just say it's a speed now. Now for A, the A will be moving, species A will be moving with the velocity of VA. Similarly, B, the squares will be moving with the velocity of VB. Okay. Individually, species may be moving with the velocity of VA and VB, and also based upon the concentration. For example, take a particular section here. Okay. In this section, say x1, if the concentration of the species A is higher than compared to say a section x2, okay, here the concentration is less. So x1 you have a higher concentration of A, x2 you have a lower concentration, because there is a decrease in the gradient, okay, the mass fraction basically. The gradient is favorable for the diffusional transport of A in the x direction. So it has its own velocity. So the flux of A is nothing but the product of the density of A, which is nothing but mass fraction into the mixture density, will be the density of A into the velocity of species A. Okay. So that is the left hand side, the mass flux, the mass flux of the species A, that is due to two components. Okay. One is the bulk velocity. The first component is the bulk velocity. The mixture itself is moving with a velocity of V, capital V, and that transports the species A. So what is the total mixture velocity? If total density, total flux of the mixture is rho, the mixture density into the mixture velocity V. So rho V, okay, rho times capital V will be the total flux, mass flux of the mixture. Here we have mixture density and mixture velocity. Now rho A into V will be the convective flux of species A, that is the mass flux of species A associated with the flow of the bulk fluid or the mixture. So that is rho A into V. We can also write this as rho into YA into V will be equal to rho A into V. Okay. So that is the first term. Second term, as I told you, is the diffusional transport, the mass flow rate of A associated with diffusion, that is represented here by the concentration gradient. As I told you in section 1 x1, the concentration of A may be higher, and in section x2 it may be lower. It may be otherwise also. If you can also assume that the concentration of A can be higher at x2 and lower at x1. That means the species can preferably diffuse in this. It may be bulk transport may be in positive x direction, but the diffusion can be in the other direction also. So that is also possible. So, if you take that scenario, the second term here represents that in the direction of negative gradient of concentration, or in this case mass fraction gradient, the species A diffuses in the direction of negative gradient. Okay. For example, if x2 has a higher concentration than x1, then the transport due to diffusion will be in the negative x direction. Okay. So, this is called ordinary Fick's law. Fick's law incorporating ordinary diffusion. So, this concentration gradient based diffusion is called ordinary diffusion. Okay. So, now this is the important statement where you have a mass flux of species A represented as the sum of mass flux of species A due to the bulk motion of the mixture plus the mass flow rate of the species A due to diffusion because of the concentration gradient represented here by the mass fraction gradient. Okay. So, the species velocity is Va, density of the species A is rho A, and DAB is called binary diffusivity, which is a property of any pair of species A and B, and DAB as a unit of meter square per second. It is a diffusion coefficient basically, and it is a property. Okay. And the diffusive transport of species A is dependent on the mass fraction gradient, or in general concentration gradient of the species A. So, this is very important. So, individually you have to have this statement written for all the species A, B. So, you need not consider all the species. If you have n species, capital N number of species in a mixture, then we have to resolve for at least n minus 1 species. Okay. Now, binary diffusivity DAB is the property of the binary mixture A. So, constituted by any two species A and B. Okay. And it has a unit of meter square per second, and this is evaluated by using fundamental principles of kinetic theory of gases like thermal conductivity, etc. We can also have a theoretical basis to evaluate this. It can also be measured and validated, and it is a function of temperature and pressure. Okay. Basically, it is a function of molecular weight also. Okay. If the for example, if you have a pair of species, say hydrogen and oxygen, okay, oxygen and hydrogen. If so, you can say hydrogen is very light species. So, the molecular weight of this mixture is actually very low because of the hydrogen presence. So, what happens, you can see that diffusivity will be very high. On the other hand, if you take, say, for example, LPG is very LPG, take one of the constituent of LPG, say butane. Okay. So, the molecular weight is higher. So, butane, carbon dioxide, where the molecular weight is 44, etc., you can see that the diffusivity will be lower. The heavier be the species, the diffusivity will be lesser. And this is a fundamental property, DAB is a fundamental property which says the rate at which a particular species A will diffuse into B. And for this is same for the otherwise, like for example, when B diffuses into A, the rate at which B diffuses into A will be same as the rate at which A diffuses into B. So, we can prove that DBA. So, first B, if you write B in the suffix first, that means B is diffusing into A. Okay. So, the rate at which B is diffusing into A will be same as the rate at which A is diffusing into B. A species cannot diffuse into itself. So, that means that DAA or DBB will be equal to 0. So, if only single component, only one species is there, okay, single component, okay, oxygen, carbon dioxide, etc. In that case, there is no diffusion at all. Okay. A single component species does not have any diffusion, only by convected it can flow. So, this is very important. So, that is what the additional component which is coming in a multi-component mixture is the diffusion of the species due to the concentration gradient. So, this is we have to at least resolve this for our problems. Okay. And this binary diffusivity is a fundamental property. Any property like say K, mu, etc. This is also another property, and this is a transport coefficient, diffusion coefficient. So, DAB is a mass diffusion coefficient. Okay. Then mixture velocity or bulk velocity capital V is also called mass average velocity. See, please understand that we are writing the concentration gradient in terms of mass fraction here. In the previous slide, what we have written is in terms of mass fraction. So, what you end up in getting is the mass average velocity here, the mixture velocity. This is the velocity which we can measure. See, for example, the mixture is flowing, okay, oxygen, nitrogen, carbon dioxide, this mixture, some proportions of these species involved in the mixture is flowing from in a duct, okay, in one dimensional x direction, it is just flowing in a duct, within a duct. So, now you put a probe like petard tube and measure the velocity, okay. So, the velocity what you measure is only the mixture velocity. At any point if you measure the velocity, it will be only the mixture velocity. This velocity is actually contributed by all the species velocities. So, for example, in the binary mixture, we can write rho v equal to rho a Va plus rho b Vb. Okay. Now, this the total mass flux of the mixture, it is a mass conservation. Total mass flux of the mixture rho into capital V, that rho is the mixture density, will be equal to the mass flux of species A, rho A Va plus the mass flux of species B, rho B into Vb. So, from this definition we can write the mixture velocity capital V as rho A Va plus rho B Vb divided by density, and this is the velocity which we will measure. Or if you want to solve the flow using CFD, this is what you will solve using the momentum continuity momentum equations. Okay. So, this is called mixture velocity or mass average velocity. So, this is very important. So, this you can measure or you can calculate using any equation. So, this is very important velocity. Okay. Now, if you want to write this in terms of mole fractions etc., then instead of mass average velocity it will be mole average velocities. Okay. So, instead of density, concentrations will appear there, concentration, that is, see, density is kg per meter cube. You will have, if you write in terms of concentration, then you can write the concentration of the mixture C into the velocity, I will say V over at bar. So, this concentration of mixture into the velocity of the mixture. Now, I am putting V over at bar to represent that this is a molar based calculation. So, this will be equal to concentration of A into species velocity of A plus concentration of B into species velocity of B. So, this is the concentration based conservation which we can write. Okay. So, it is general practice to write the conservation in terms of mass. So, this we need not consider. Okay. So, this is the mass average velocity. Now, as I told you, each species, if you go to the previous slide, you can see that each species here is moving its own with its own velocity Va and Vb. So, A moves with the velocity of Va and the B moves with the velocity of Vb. It may be in a multi direction also, it is not need not be in one direction. So, that may be vector, okay. But we can extend this one dimensional to multi-dimensional later. Okay. Apart from this, it is also diffused from high concentration zone to the lower concentration zone, and this can oppose, the diffusion can oppose the convection and vice versa. Now, species A and B travel with their respective species velocities small va and small v suffix b, and it is not possible to measure this. Okay. So, then how will you resolve this equation? Okay. That is what we are coming to do. See, what you have to do is we can measure the first term. So, that is density can be measured or it can be calculated. Similarly, mass fractions, if you know, then we can calculate the mass fractions. We can actually take out the species at a particular point and see what is the concentrations of each species in the mixture there at that point. Similarly, velocity at the point can be measured. Okay, now if you have a binary mixture, then the DAB can be evaluated using theoretical approach. So you have some values based upon some correlations giving you the value of DAB. Now concentration at 2 points if you can measure, then you can also know the concentration gradient. So what we actually measure is the right hand side you can measure or calculate the quantities in the right hand side and evaluate the mass flux of species A. So that is what is going to be used in the species conservation equations later. So this is not, but we cannot measure this or calculate this directly. You have to calculate this using the expression shown before, or you can measure only the mixture velocity capital V, calculate the diffusion part and calculate the species part, species velocity. Okay. Now coming to the second term in the right hand side of the previous equation, diffusional flux of A is proportional to the gradient of the mass fraction. Here I am writing in terms of gradient of mass fraction. As I told you, concentration gradient can also be used, and the constant of proportionality is nothing but actually I will not take the minus here. So rho times DAB, this product, that is the key here, that is a key proportionality constant here, and this is analogous to the heat flow where thermal conductivity will be the constant of proportionality, thermal conductivity, and the gradient is as such negative, representing that the flow of the species A takes place from the higher concentration to the lower concentration, exactly same as the heat flow occurring from a higher temperature point to the lower temperature point. Okay. So diffusion, that is called heat diffusion, this is called mass diffusion. Okay. So that is very important to understand this. So we can also, you can see that rho into DAB will be equal to K by Cp. We can show this. Okay. Okay. Now let us write the Fick's law. As we wrote for the species A, let us write that for the species B. So the net flux of species B, rho B, the density of species B into its species velocity Vb, small v suffix b, will be equal to the mixture density into capital V, the mixture velocity, into mass fraction of the species B, Yb, minus, or you can write plus, you can also write here this plus and take the minus inside this gradient here. So mixture density. Now I am writing the diffusion coefficient or the binary diffusivity the other way, the rate at which the species B diffuses into A, that is dBA, but we know that dBA will be equal to dAB in a binary scenario. So that into the gradient of B in the x direction. So again it represents that if the concentration gradient decreases or the Yb is higher at x1 and lower at x2, then the flow will take place from x1 to x2. Okay. So now you have a similar equation for A and this is the equation for B, add these two. So rho A VA, left hand side will be rho A VA, the net mass flux of A, plus rho B VB will be net mass flux of B, that will be equal to rho V times Ya plus Yb, that this is equal to 1, because in a binary mixture the sum of mass fractions of each species will be equal to 1. So that is unity. So now by definition rho A VA plus rho V VB equal to rho V. So that means that these terms here will cancel each other. So this term here will go to 0. That means the diffusion flux of A plus the diffusion flux of B. In a binary mixture there are two species A and B. The diffusion flux of A plus diffusion flux of B is equal to 0, or we can say that the sum of diffusional fluxes of all the species is equal to 0. In a mixture if there are n species, add the diffusion flux of all the species, that should be equal to 0. Okay. So this is for multi-component mixture. You can extend this binary to any multi-component mixture, okay, where there are more than two species. So this is one of the important thing we should, this is actually used as constraint to derive some important aspects of the flow. So, this is very important.